Hey everyone, and welcome to this explainer. Okay, so if you have ever stared at a complex Java application and wondered, how on earth it manages to juggle 100 different tasks at the exact same time, well, you are in the right place. Or maybe you're gearing up for a massive technical interview and you just really need a rock-solid mental model of concurrency, we've got you covered. Today, we are going to completely demystify exactly how Java threads work internally. We're going to take all those really complex mechanics of multithreading and break them down into crystal clear, easy to understand concepts. By the end of this, you'll be ready to ace that interview and, honestly, just write much better code.
To really set the stage here, I want you to think about an application you probably use literally every single day, your web browser. How does it manage to play a high-definition video, securely download a massive zip file in the background, and load up new interactive web pages all at the exact same time? Have you ever thought about that? How can one single application juggle so many incredibly heavy tasks concurrently without just totally freezing up on you? Well, it feels completely seamless to us as users, but under the hood, it is an absolute marvel of software engineering.
All right, let's dive right into this. Here's our roadmap for today. First, we'll cover what Java threads actually are. Second, we'll look at process versus thread. Third, creating your very first thread. Fourth, the thread lifecycle. And finally, number 5, the multi-threading trade-off. So kicking things off with section 1, what are Java threads? The multitasking illusion. At its absolute core, a thread is basically the smallest possible unit of execution within a program. So multi-threading, then, is the ability to execute multiple threads concurrently inside a single process, to perform tasks simultaneously. This is exactly what allows applications, like that web browser we just talked about, to run all those different tasks at once. You see, the browser itself is the main process, but the video player, that's one thread. The file downloader is a completely separate thread, and the web page loader is yet another one. By using multi-threading, the process orchestrates all of these tiny little units of execution so they happen at the exact same time. Moving on to section 2, process versus thread, the heavy versus light matchup. Now, beginners mix these two up constantly, but the differences are literally night and day. Think of a process as an entirely independent program. It's considered heavyweight because it actually requires its very own dedicated memory space. And because of all that strict isolation, spinning up and switching between processes is just much slower. A thread, on the other hand, is just a small unit living inside that process. It's super lightweight. And here's the kicker. Threads actually share memory with the other threads living inside that exact same process. Because they aren't dragging around all that extra baggage, they are significantly faster to create, manage, and execute.
All right, section 3, creating your first thread, the birth of a thread.
So, how do we actually bring one of these threads into existence in our Java code? Well, there are 2 main ways to do this. You can either extend the thread class, which just means your custom class inherits directly from java.lang.thread, or you can implement the Runnable interface, meaning your class implements java.lang.runnable. Now, both of these are going to get you a working thread, for sure, but they have very, very different implications for your software's overall architecture. Okay, huge interview alert right here. If you're ever asked, implementing Runnable is almost always the preferred method. Why? Well, it's because Java only supports single inheritance. If your class extends the thread class, it's completely locked in. It absolutely cannot extend any other class. But by implementing the Runnable interface instead, you're separating the task itself from the actual thread mechanism. That means your class is still totally free to extend something else, which makes your overall design significantly more flexible. It's a real game changer. Let's keep rolling. Section 4, the thread lifecycle, the 5-stage journey. A thread doesn't just run wildly forever. It actually passes through some very specific, tightly managed states. Let's trace its journey. It all begins in the new state. This is when the thread object is created in your code, but you haven't actually called the start method just yet. Second, once you finally do call start, it enters the runnable state. It's ready to go, just sitting there eagerly waiting for the Java Virtual Machine, the JVM, to allocate it some precious CPU time. Third is the running state, where the CPU is actively executing the code inside your run method. Fourth, the thread might hit a blocked or waiting state, which temporarily pauses its execution. And finally, stage 5 is terminated. This means the run method has fully completed its execution, or maybe it threw an uncaught exception, and the thread is officially dead. Now this brings us to another massive interview question, so pay attention to this one. The stark difference between calling start versus calling run directly.
If you call start, then yes, it actually creates a brand new thread and your task runs concurrently. But if you make the rookie mistake of just calling the run method directly, no new thread is created. It just executes the code synchronously, exactly like a normal method call on the main thread, which entirely defeats the whole purpose of multi-threading.
Let's quickly jump back to that fourth lifecycle stage, blocked or waiting. How exactly does a thread get forced into a temporary stop? Well, it happens if the thread is waiting for a lock so it can access synchronized code. It also happens if you explicitly tell it to wait using the wait method, or if you tell it to sleep. For example, using thread.sleep 3000 to forcefully pause that specific thread for exactly 3 seconds. It can also happen if it's waiting for another thread to finish its job by using the join method. So, imagine you have multiple threads sitting there in the runnable state. How on earth does the system know which one to pick next? Well, threads have priorities. In Java, this priority ranges on a simple scale from 1 to 10. You have min priority at 1, norm priority, which is the default, at 5, and max priority sitting all the way up at 10.
But guys, here is the absolutely crucial point. Priority is only a hint to the JVM scheduler. I repeat, it does not guarantee execution order. You might set a thread to a priority of 10, completely expecting it to always run first, but the scheduling is ultimately handled by the highly unpredictable JVM and your host operating system. Because of this, you can basically never, ever rely on exact execution sequences just based on priority alone. Which brings us to our final section, Section 5, the multi-threading trade-off, the pros and cons. So, if unpredictable execution is so difficult to manage, why do we even go through all this trouble in the first place? Let's rapid-fire the benefits. Multi-threading dramatically improves performance. It provides much better CPU utilization by keeping the processor busy instead of just letting it sit idle. It allows for much faster overall execution and enables parallel tasks. Just think back to our web browser example from the very beginning. Multi-threading is the exact mechanism that keeps our applications highly responsive to our clicks and inputs, while it does all the heavy lifting in the background. But of course, this brilliantly illustrates the dark side of multi-threading too. The disadvantages. If you aren't incredibly careful, multi-threaded applications are notoriously complex to develop and just a complete nightmare to debug. You run into nasty synchronization issues. You encounter race conditions where threads actively compete for data and end up corrupting it. You see increased memory usage, and honestly, worst of all, deadlocks. That's where threads freeze up permanently because they are waiting on resources held by each other. It is a true headache for literally any developer out there. Which leaves us with this final provocative thought to ponder today. Given the massive headaches of synchronization, race conditions, and debugging, is the blistering speed and responsiveness of a multi-threaded application always worth the risk of a catastrophic deadlock? It's really the ultimate balancing act in software engineering, isn't it? But understanding exactly how these internal threads work is your very first step in mastering that balance. Keep exploring, keep coding, and thanks so much for joining this explainer.